Hello, good morning everyone. I am Sravanthi from Aeronautical department. So today we will be seeing another topic in our flight vehicle design subject. In the last class we have seen about the airfoil section and we have done a numerical. We will continue with the same and then we will proceed to the wing steps and also its design selection. Okay. Another problem of the airfoil. So an aerofoil, we need to select an ARC aerofoil section for the wing, right? It is a non-maneuverable jet aircraft and it has got some parameters. Some parameters are given here. Mass is given in terms of kg. In the previous class, we have done the same selection of an aerofoil, but in a different manner, right? So they have given a different parameters and they have asked us to characterize the airfoil selection. So here, in a different way, right? We are doing another problem. So in terms of mass is given, then S is given, then the speed of it is also given, right? At sea level it is given. Then high lift devices, they are saying it as a split flap. For a split flap, then the CL is going to be 0.8, right? So for that we need to select an airfoil section. So first of all, we will find out all the lift coefficient, right? So we have seen these steps yesterday. What are the different things that need to be found out, right? Found out. Then we have done few ideal lift coefficients and the other maximum lift coefficients yesterday in yesterday's problem also. So even for this numerical, we are going to find out if W is not given or W average is not given, right? Suppose it is not given, then how did we found out? By taking the final plus initial by 2, right? So that is what we have done. But that was in a previous problem, and for that, in order to find out this WF and WI, I have to calculate the complete takeoff estimation as we have done in the initially, right? Initial numericals we have solved for range trade-off and payload trade-off, right? So there we have to find out all Wx by W naught. Then we need to find out fuel, right? Fuel fraction. Then we need to find out the empty weight fraction. Then make a iteration table, guess the weight, then find out the calculated weight of it, right? So after doing all of those, we come to a point where what is the calculated weight, right? So those things have to be kept here for W average. But here in this numerical, directly the mass is been given saying 4000 kg, right? So we directly take the data. So CLC is going to be 2W by rho V square S, right? Then this comes from the lift equation. So from the lift equation, we know L is equal to W for a steady level flight, or in terms of cruise, we are considering that. So from there, we can write CLC 2W by rho V square S to W is given 4000, right? In terms of kg is given. So we are adding a gravity here. Then density is 0.9, right? Then speed is also we have taken from the same given data. Then S is also being calculated here, right? So therefore the CLC is going to be 0.176. Then for a wing, it is going to be wing ideal lift coefficient is going to be 0.176 by 0.95. Then again, this particular CLI is going to be the CLCW by 0.9, right? So we calculate all the ideal lift coefficient, then we come to all the maximum lift coefficient in terms of aircraft, in terms of wing, in terms of airfoil, gross weight, and finally we come to a CL max, right? So therefore again we calculate the CL max also, which is 1.9, right? Then for a wing, the maximum lift coefficient 2, then gross is going to be the wing by 0.9 is going to be 2.233. Then finally the maximum lift coefficient is going to be the gross of maximum CL minus delta CL max when high lift devices of a split flap is considered, because our question is saying it is going to be a split flap, right? So therefore for a split flap, it is already mentioned it is 0.8. So we don't have to go and check the historical trends. So we directly know it is 0.8. So therefore maximum CL is going to be 1.433 here, right? So with all the data of ideal lift coefficient and maximum lift coefficient, I try to select what is the best airfoil, right? So therefore its ideal lift coefficient is 0.2 and the maximum lift is 1.433. right? So for these data that we have calculated, now we are going to find out what is the best one, right? So what is the best one can be chosen from the different NACA series family. So from there, if we see, so from there, this is the chart that has been given, right? So this I have taken from the Raymer textbook. So ideal lift coefficient versus maximum lift coefficient. These are the data that we have obtained by calculating the step-by-step procedure of how to select an airfoil, right? So what is the ideal lift coefficient we have obtained? 0.2, and the maximum lift coefficient is 1.433, right? So 0.2 ideal lift coefficient on x-axis standing 0.2, and on the y-axis we have maximum lift coefficient 1.433. So in this regime, so we consider all the series which are going to be relatively matching our particular numerical, right? So all these data have been kept here, right? So all the things that are going to match our design are this particular series, 1 2 3 4 5 5 we have collected, saying that these are the matching design requirements, right? So one is 633 218, then the other is 64210, then the other is 661 212, 662 215, and 653 218, right? So these are the most closely relatable to the airfoil that we are going to select, and for the data that has been calculated, right? So we are going to compare all these five series, and all five all all five, and we are going to take out what is the best airfoil, right? So that data can be shown here. Yeah, so this is the data of all the five different uh, series that we have taken from the graph of ideal lift coefficient versus maximum lift coefficient, right? So it is showing a minimum drag coefficient, then CMO, then the alpha S, then the alpha 0, then CL by CD max, and stall quality, right? With all the data that I have, then I choose what is best for me according to the application, or according to what I want, or what is the requirement, based on the requirement, right? So therefore, for a 63218, then we have minimum drag coefficient to be this much, 0.005, then 64210, the minimum drag coefficient is 0.04, and it is a little bit decreasing, and then we have a highly 0.004 again, right? So then for this angle is going to be the highest for the 653 16, right? Then CL by CD max is going to be the maximum for the fifth one here, right? And this varies depending on the requirement what you want. Do you really want it to be a sharp, or if it is not sharp, then if it is moderate, then I would be satisfied with whatever the other parameters that I have to meet, right? So that has been computed and kept here. So for an ACA series of 661212, it has the highest maximum speed because it has the lowest minimum drag coefficient, right? Highest speed because it has the lowest minimum drag coefficient, right? Then we have a 653218, which yields for a lowest stall speed because it has the highest stalling angle of 16 degrees. So 653218. Yeah. Okay. It has the highest stall angle. Then we are concluding that 653218 has the highest endurance because it has the CLCD max to be highest. Okay. Then 633218 is the safest flight due to which dorsal stall quality. Sorry, right? So this one. Then this NACA airfoil series of 633, 218, 215, and 218 deliver the lowest two problems in flight due to the lowest CMO. Right. So now it is not necessary that I have to pick only according to the lowest stall speed, or according to the highest endurance, according to stall quality, depending on the problem that is given, depending on the requirement that is being asked by the customer. Accordingly, I am going to choose the airfoil, and that has to be designed, right, depending on the requirements or what is actually wanted, right? So then if I want this kind, if I want a dorsal quality, then I would be happy with this particular series of airfoil. If otherwise, if I want a very sharp one, then I would go for within the region which is having all the other different parameters to be giving a better option. or a better value, then I will go for that, right? So that is how we select an airfoil according to the problem definition, right? So first of all, we go and calculate all the ideal lift coefficients for aircraft, for wing, for airfoil. Then we calculate all the maximum lift coefficients for same aircraft, wing and airfoil. Then we also include the high lift devices. We consider that, and finally we come to a conclusion of ideal lift coefficient and maximum lift coefficient. And with that, we are going to choose in that particular regime what are the different series that are going to match our requirements, and in those 5 or 6 series of series we are going to choose according to the requirement that has been provided. Okay, so therefore the question is saying that it is a non-maneuverable GA aircraft, then I don't want a stall quality to be sharp, right? So therefore, if I don't want a sharp, then all the sharpens can be neglected here, right? 212 and 215 can be neglected. If I'm neglecting, then it is safety. If we're talking in terms of a commercial airways, then safety is the most important priority. So for in terms of safety, then it is going to be the best option. Otherwise, in terms of different things, then the different, it is the lowest CD minimum, I would prefer the other one, right? So in such a way, according to what you want, in that way we go and choose that particular type of the airfoil, right? So that is how we solve or we select the airfoil according to the steps that we follow, right? So the next is the same, similar to the airfoil selection. We need to have a selection of or a design of the wing accordingly by selecting the different parameters to it, right? So during the wing design process, there are 18 parameters that must be determined, right? So all those 18 parameters are wing reference or wing platform, or we simply call it as SW, right? Then the number of wings, right? Then a vertical position relative to the fuselage, a high or mid or a low wing. Then horizontal position relative to the fuselage. Then a cross section or airfoil, we say aspect ratio, taper ratio, tip chord, root chord. Now all these detailing we have done in the previous classes, right? When we were talking about the wing. Then mean aerodynamic chord, span, its twist angle, sweep angle, dihedral angle, wing incidence angle, high lift devices, ailerons and other wing accessories, right? So all these are the 18 parameters that we need to determine when you're going to design a wing. And a wing design procedure has been shown here. We are going to identify and prioritize wing design requirements, right? Its performance based on its performance, its stability, producibility, its operational requirements, its cost, and its flight safety, right? So for that, select number of the wings, right? Then select a wing vertical location. Then for the high lift devices, we are going to select. Then determine the sweep and the dihedral angles. Then you go and select or design your wing airfoil section. Then other parameters like aspect ratio, incidence angle, and so forth. Then calculating the lift, drag, and pitching moments. Then when you go and do all of these things, if you are satisfying with all the requirements, then yes, we will go and optimize it for the further next level. Or if it is not satisfying, or if the requirements are not met as it has to be, then it is a no. Then we go on again, change the different parameters, change the number of wings, or change the whatever the high lift devices that has been chosen, let it be another one, or whatever the sweep or whatever the airfoil selection, airfoil has been selected, right? So do a little minor changes over then, and again come back and see if the requirements are met, if it is satisfied. Then finally we go and optimize it and we calculate it. Okay, so that is how we follow a step-by-step procedure in wing designing. So step one is going to be divide one half of the wing into several segments or end segments, right? So if I have this particular wing, then I'm going to divide it into a number of a small segments, right? So an example shown here. So I'm dividing it into these many segments, right? Then the segments along the semi-span could have a equal span, but it is recommended to have a small segments, right? So we recommend let it be a smaller ones in the region closer to the tip, right? So again, when you are, even though if it is a whole complete wing, right? Even though it is being cut short and it is made a smaller segments, the unique chord and may have a unique span to it, right? Then second is going to be calculate the corresponding angle theta for each section, right? So when you are going to divide it, then I'm going to have a separate angle, so that all need to be calculated for all the different sections or segments that has been divided. Then these angles are going to be the function of lift distribution along the semi-span. Then each angle is defined as the angle between the horizontal axis and the intersection between the lift distribution curve and the segment line, right? So these angles are going to be horizontal intersection between these segment lines. Then the angle theta varies between 0 for the last segment and a number of close to 90 degrees for the first segment, right? Then we're going to solve it, right? So solving by using a Prandtl equation. So right, we also call it the lifting line equation. So we have that this particular equation. We're going to solve it for all of those n segments, right? N is going to be number of segments. Alpha is going to be the segment's angle of attack here. Alpha naught is going to be the zero lift angle of attack, and coefficients an are the intermediate unknowns, right? So we are going to calculate all of these things, right? So CI again segments mean geometric or CL alpha is the segment's lift curve slope, right? Then if the wing is going to have a twist, then the twist angle must be applied to all of the segments, right? So similarly, according to the steps that we're following, we calculate all the other things. Then determine the each segment's lift coefficient. Then you have how many of segments you have been divided in segments. We are going to calculate the CL for it, right? Then we are going to plot the variation of each segment's lift CL versus its semi-span. Okay. Then finally determine its wing lift coefficient, wing total lift coefficient. Okay. So that is for pi and with respect to aspect ratio and with respect to A1, right? A1 to AN. So then for that, we are going to select number of wings. So first of all, what is it we are going to do? First of all, we are going to divide it, right? You divide it entirely into small sections and let it be a very small. Then calculate all the corresponding angles to it, right? Then finally, according to the Prandtl equation, we will find all of those things, right? Then we will determine the segment's lift coefficient. Then determine the total lift coefficient to it. Okay. So for that, select number of wings, monoplane, biplane. Then we're going to select its location, high, mid, or low. Then wing configuration, if it is a straight or if it is going to be a swept one, if it is going to be a tapered one, if it is going to be a delta one, right? Then we're going to calculate the average aircraft weight, right? So this procedure is going to be repeated because my airfoil selection is going to come in between of these things as we have seen in the flow chart. Yeah. So I have a selection of a wing airfoil to make. So first of all, I have to complete all the procedures or all the steps of the airfoil. Yeah. So calculate the average aircraft weight. Again, we know. Again, I have to start it from the very beginning of how to calculate the takeoff weight estimation. If I don't have a precise average weight, right, then I have to calculate. It is given, then well and good, right? My work is easy, right? So WI is aircraft at the beginning of the cruise. WF is the aircraft at the end of the cruising flight. Right, then you calculate the required aircraft cruise lift coefficient, then you do your aircraft takeoff lift coefficients, then you select your high lift devices, you take the delta CL of that high lift devices from a particular chart, right? Then determine its HLD geometry, the span, chord, and maximum deflection to it. Then you select. Now when you're done with all of the selections of maximum lift coefficient to delta CL with respect to high lift devices or ideal lift coefficient value, then I consider all of these things and I select a few regime in that area, right? I select up all different NACA series in that particular area, and I, according to the particular table, I consider what according to the requirement I select what is that I want, what is the specified type of the series I want in me. I want to have it, right? So then we are going to find out the other wing parameters like aspect ratio, taper ratio, twist angle, right? Then finally calculate the lift distribution at the cruise, right? So for that we are going to use lifting line theory and CFD. Then check the lift distribution cruise. At cruise is elliptic. When you're trying to draw a particular calculate the lift distribution at the cruise, when you're trying to draw it, if it is elliptic, then it's fine. Otherwise, we return to a step of 13 and change few parameters, right? Then then again we go and calculate the wing lift at the cruise. Then the wing lift coefficient at the cruise must be equal to the required cruise lift coefficient. If not, again you go and change little parameters, change your wing setting angle, then again calculate all of those things, calculate your parameters again select it, right? So if everything is working well, if all the parameters are going to be a satisfied level, then well and good. If not, if you feel that something is going to be misplaced, then we go and change few parameters and then again try to redo it again. Then only we try to optimize things, right? So if aspect ratios are not mentioned to me in the question, then I have a data, right? So historical trends are there, so taken from the Raymer textbook again. So we have all of this data, so we can select what based on the type of the aircraft, mostly it is general aviation or a home built one, then we consider to take the aspect ratio accordingly, right? Then again aspect ratio with respect to this particular angle, right? So you consider all of these things and try to do a numerical, right? So we have a numerical. So once just we'll go through the bloom. So okay, so what is it we are going to do? We are going to select number of wings, then the location, then the configuration, then you will calculate the average weight, then the cruise lift coefficient weight, then aircraft total lift coefficient, then make a high lift device, then you find out that, then you bring out your ideal lift coefficient and maximum lift coefficient, then calculate your lift distribution. It has to be elliptic, right? So determine a numerical for the wing design. So determine and plot the lift distribution for a wing given the following characteristics. So they want us to divide the half of the wing into 10 sections. So 10 segments here. So S is 25 meters square and aspect ratio is 8. Lambda is 0.6, wing incidence 2 degrees, alpha t is minus 1 degrees, aerofoil section is already mentioned. So it is an ARCA 63209. And if the aircraft is flying at an altitude of 5000 meters, so at the 5000 meters, I should be able to calculate what is density. Density is already given to me. Density at 5000 meters is 0.736 kg per meter cube, a speed of 180 knots. Okay, so then they're asking us to find out how much lift is going to be produced, right? So now based on this particular graph, we are taking this particular data. Okay, and now this we can easily do it in the MATLAB, right? So we all have to do is just write a code to it, right? Take all the parameters that has been mentioned in the question and all the required data that is essential in order to plot this lift distribution, right? So we put all of those things in the mat code and then we do it, right? So when you try to put all of these things and this is how we are going to get a lift distribution semi-span versus lift coefficient. Okay, yeah, so this is the lift distribution of the wing. So this is how we should be able to calculate the wing design problem, right? So whether it is a wing designing or a selection of an airfoil, right? So first of all, we will understand what are the different step-by-step procedures we have, and then we try to modulate accordingly, right? So for any given question, if the question is stating only the parameters, right? Only about the aircraft weight or its payload or the passenger weight, then I first of all calculate my takeoff estimation, right? I come up with all the segment fractions of it. I calculate the fuel fraction, then empty weight fraction. I try to make iterations by guessing it, right? Then I have my final weights and initial weights, right? So with that, I try to make the average of it. Then find the aircraft lift coefficient, or in terms of ideally for aircraft or for wing or for aerofoil. Then for a maximum, I find out, then high lift devices have been considered, and for that we take a choice of in between, if it is 0.7 to 0.9, and what is your better choice. Then upon that, you make few different series which can be suitable to you, and that should be your best airfoil selection. Or with that comes the wing design. Then accordingly we follow the same steps, but not same. There are some you divide your segment into it and you apply your Prandtl lifting line theory, then you calculate certain things, and then finally the question has been direct here, right? If the question is not direct also, we try to find out which is the best airfoil, then later on we make all the different calculations here, right? So in the question it has been made easy. So we just simply have to mention the other parameters, what are all I require, all the 18 parameters that I want to find out, make all of them, right? Put the data and collect the data and put it in a MATLAB code and give a for loop to it and run the code. Then the code should simply give you the lift distribution, right? So this is how we are going to uh, design a wing, right? Design a wing section or select an airfoil or design an airfoil or calculate the takeoff weights, right? So this closes with the first module, right? So in the first module, all that we have learned is what are the different types of designs we have, conceptual or preliminary or detailing, right? Now that whole flight vehicle design subject will go through with the conceptual design phase itself, right? So in that we have studied all the how to estimate the weight, what are the things that are going to come under in order to find the range or endurance, if there is a loiter or if there is no loiter, right? So we have considered all of these things and have calculated few parameters and have solved few numericals with respect to commercial aircraft or a military aircraft. Then we have seen all the basic detailing about wing tail configurations or about the airfoil, right? Then with that also we have solved few one or two numericals of how to select or design airfoil or how to design a wing, right? So that closes with the second module, and the next tomorrow we will be starting with the module 2, rubber engine sizing or a fixed engine sizing. Okay. So I would like to you people to practice more of the problems, more of the numericals, right? So that should be included in the flight vehicle design laboratory, right? So that tells about how to plot your wing or how to select the airfoil or design an airfoil, right? So all those things can be seen in the laboratory sessions. Okay. So thank you.
Like, share, and subscribe. Hit the bell icon for more updates.